Hello, today we will talk about cooperative interference mitigation and handover management for heterogeneous cloud small cell network based on paper with the same name from IEEE Wireless Communication magazine. First of all, let me give you a simple overview of the whole presentation. In the first section, I will simply introduce some background knowledge such as some concepts and state of the art about this topic. Then I will point out the limitations and challenges which exist in this field and to further propose a new research focus. And then introduce a proposal scheme which is presented in this paper. In this part, I will describe from 4 aspects. In the end, we will give an evaluation to conclude the whole paper. Nowadays, the wireless communication systems offers some requirements. Explosive growth of user data requirements. Macro-cell data traffic is too heavy to afford. Low power consumption and optimize section to reduce CAPEX and OPEX. Improve the coverage and capacity of cell edge users and hotspots. Some concept. Miracle cell, a cell in mobile phone network that provides radio coverage served by a high-power cellular-based station. Microcell is used to describe the widest range of cell size, which usually refer to a range of a few tens of kilometers. Small cells. Low-powered radio access nodes that operate in licensed and unlicensed spectrum that have a range of 10 meters to 1 or 2 kilometers. Small cell may encompass microcell, picocell, and femtocells. Elaboration of a heterogeneous small cell network. Low-power small cells work together with microcells by exploiting the spatial reuse of spectrum. Which is helpful to improve the coverage and capacity of cell edge users and hotspots. Small cells offload most of the data traffic from microcells to ease the data traffic pressures. Mental basis station fixture, cell installing, and cell operating, which can reduce mobile operators' CAPX and OPEX. Operation of cold radio access network, a promising wireless network architecture in 5G networks, was first proposed by the China Mobile Research Institute. Baseband process is centralized in baseband union pool, while RF process is distributed in a remote radio head. Few BBUs are required. Consumed power is lowered, which helpful to reduce both CAPX and OPX for mobile operators. The requirement of wireless communication systems, they are a promising solution. Heterogeneous cloud small cell network, which is a combination of the heterogeneous small cell network and the CRAN. It has some advantages, lowering the number of BBUs in densely deployed heterogeneous small cell network. BBUs can be added and upgraded easily in BBU tunes. Radio resource management functions are promoted with little delay. In the literature, HCSNet has been studied extensively. State-of-the-art research results and challenges were served for heterogeneous CRANs, and promising case technologies were investigated to improve both spectral and energy efficiency. But they also have some limitation in the existing HCNet studies. 2 of them are the clustering of combined cooperative interfaces mitigation for an HCS net, screamless mobility handover management of users for the HCS net. In this paper, the author proposed some new research focus. One is a comp-based cooperative interference mitigation for the HCS net, and another one is handover management. He also proposed some proposal scheme, network architecture of a cloud computing-based HCS net, and another is effective comp clustering scheme in HCS net using affinity propagation. And the third one is handover management scheme, which including handover procedures. Let's show you the HCS net architecture in details. The HCS net architecture is combined of microcells, which is referred to MRRH, and small cells is referred to SRRH, and the component is deployed. And the BBU pool will have the function to realize the resource management, control capabilities, and handover management. And the connection. The different BBU pools is connection by the X2 interface, and the further links is connection by the millimeter wave radius. This is a picture of cloud architecture for interface mitigation. The key technology of this model is combined technology. And this is a picture about the AP clustering-based cloud comp scheme in HCS net. This is a model definition of AP clustering-based cloud common skill in the HCS net.
About evaluation of the AP clustering-based cloud comp scheme in HCSNet, this figure is the spectrum efficiency CDF curve of edge users. It shows that for study camp schemes achieve higher spectrum efficiency than non-camp scheme, and the APPC scheme provides better spectrum efficiency for the edge user than the other schemes. And this figure compares the runtime of different schemes on the increasing side of cell in network. It shows that all schemes increase when the number of RH increase, and the runtime of APPC comps is the lowest when the number of small cells is greater than 19. Handover management is one of the key techniques to meet users' quality of service requirements in mobile communications. In a densely deployed HCS too many handover will cause a heavy burden on front haul and core network. Mobility handover, RLF, and unnecessary handover may happen because of the small size of SRH coverage and severe co-channel interference. But in the CRAN-enabled HCSNet, it can reduce the interrupt and handover delay by using the BBC pool. Handover management in the HCSNet architecture is different from that in the existing heterogeneous network architecture, and because of that, the HCSNet related handover procedure should be modified in both SRH to SRH and NRH to SRH handover. In this procedure, many management functions, for example, related resource handover related mobility, have to move to BBU pool. And because no existing research purpose a handover procedure between BBU pools in a HCS net, and so the author introduced the inter-BBU pool MRH to SRH handover call flow based on the HCS net architecture. In the inter-BBU pool handover procedure between SRH and MRH in HCSNet, when a MRH to SRH handover happens, the source MRH will send the measurement control messenger to user, and then send URL allocation to user to give the user related authority. After receive that, user will return the measurement reports to source MRH. The source MRH will forward this message to source BBU pool, and then the BBU pool will make the HO decision by these reports. And after that, the source BBU pool will then send the handover request to target BBU pool. The target BBU pool will proceed the admission control process. After that, the handover request ACK will be sent to source BBU pool and forwarded to the source SRH. At the same time, the mobility control information will send to source MRH from source BBU pool. This mobility control information will be forwarded to user. Then user will detach from the cell and synchronize to the target SRH. The target SRH will send URL, location, and TA to user. After that, user will send reconnect and reconfigure completed information to target SRH, and target SRH forwarded to target BBU pool. Target BBU pool will then send path switch request to source BBU pool, and in order to respond to this request, source BBU pool have to send user plan update request to core network. The core network will switch new DL path for user and send the user plan update response to the source BBU pool. Source BBU pool then send the path switch request ACK to target BBU pool. After confirm that the user path has switched, the target BBU pool will send user context release control message to source BBU pool. And then the source BBU pool release the resource for the user. And now the whole procedure of MRH to SRH handover is completed. Due to the dense deployment of small cells, the number of handover-related RF and unnecessary handover need to be reduced. There are 5 types of undesirable handover: pinpoint handover, continuous handover, later handover, earlier handover, and wrong handover. This handover can be detected by following procedure. Firstly, RH start a timer for each user when a handover is completed from each user. Then RH stop the timer when RH receives the IF report from other RH during the time period. Finally, RH categorized RLF according to user starter after the RLF. Usually, high-speed users don't need to hand over to a small cell while low-speed users wish to do that. High-speed handover to small cell is unnecessary on traditional scheme, and a simple but effective low-complexity handover scheme is presented. And when a handover occurs, the high-speed user doesn't hand over to SRH. The medium user with real-time switch hand over to small cell while no real-time switch doesn't hand over to low-speed user hand over to the small cell. In order to verify the performance of the optimized scheme presented in this subsection, we compare the optimized scheme with the traditional handover scheme in terms of system signaling overhead in different scenarios. And this picture showed that the signaling overhead increased while call holding time increased. It's because the larger the session holding time, the bigger the possibility of cell crossing, implying a high probability of handover. And we can also observe that optimized scheme has a lower signaling overhead compared with the traditional scheme. Signaling overhead raises the proportion of mobility users. It shows that signaling overhead increases when the proportion of high mobility state user alpha increases in traditional scheme. Optimized schemes overhead decrease when alpha increase and when alpha increase close to zero, the signaling cost in the optimized algorithm decreases to zero, as the optimized scheme does not allow high-speed users unnecessary handover. The total cost of the handover is reduced. As a result, there is a big decrease in the optimized scheme in signaling overhead. This article also examines cooperative interference mitigation and handover management in the HCS net, where a cloud radio access network is combined with small cells. The comp clustering scheme can mitigate the cell edge users' interference, while handle management scheme can reduce the signal overhead of handover. And the proposed network architecture can significantly increase the capability of an HCS net while maintaining users' quality of service. About the future work, the author consider about the joint interference and as well as the self-organized HCS net architecture. And that's all. Thank you for your watching.